electron exists. Right, that's the whole point. So, for instance, if we took a look at, let's do nitrogen. How many electrons does nitrogen have? Nitrogen comes in with 7 electrons. So I want to specify the location for each of those 7 electrons. We've got a nice little picture that depicts all the possible orbitals. Where's the very first electron need to go? Even easier than 1s. I think someone said it. Very lowest energy. So we can put our very first electron in at the lowest energy. To draw out this picture every single time is going to be tedious. So we want to come up with a naming system to allow us to then write it out simply instead of drawing it. Right? That is the 1s orbital because it is 1, our lowest energy. And we only have one type. It's the s orbital. So if I'm looking at the electron configuration, it becomes 1s. Right? That would explain the location of 1 electron, but I need 7. Where's the second electron go? Also in that exact same location. So I can say that is 1s2. The first 2 electrons go into the 1s orbital. If I need to add the third electron, where's the next highest level? That then bumps up to the second energy level, which splits into 2 different types, which we can refer to, the first one being the 2s. How many electrons? I can fit 2. We move up to placing the next electron in. That now goes up to the p type. Okay? And I'd have 1s2, 2s2, 2p1. How many electrons would that be? 5. How many do I need for nitrogen? What do I need to do? Add 2 more electrons. Where's the next electron go? Which of the 2p? So I will agree in the 2p, but we have 3 possible 2p's. It's actually going to go into the unoccupied p orbitals first. Okay? So when we paired, we only paired if we didn't have an equal energy to go into. Okay? If we have an equal energy, we'll keep them unpaired. Why? What do electrons do when they get near each other? They repel. So the only reason I pair them is because they want to stay at the lower energy. If I'm at an equivalent energy, they're going to want as much space as they can. They'll fill out that space. Okay? So our configuration for nitrogen becomes 1s2, 2s2, 2p3. Make sense? Let's make this a little bit more challenging. What happens if I add 3 more electrons? What does my electron configuration become? So it becomes 1s2, 2s2, 2p6. Right? That makes sense. Is that a yes? Yeah. Okay, so now the harder question. What is the symbol for the atom that follows what we just walked through? What's that? Yeah, I'm going to shout it out. So we're hearing a couple. I heard a fluorine. So answer A, fluorine. Answer B, I heard neon. Any other answers? Just to be annoying, I'll tell you there is an answer C. Okay. We'll get to answer C in a second. Fluorine. How many electrons does fluorine have? 9. The subscripts are a number of electrons. If we add up 2 plus 2 plus 6, how many electrons do we have?
10.
We have 10 electrons. If fluorine only has 9 electrons, is fluorine correct? No. So fluorine's wrong. What's that? We'll talk about that in a second, but we aren't there yet. Okay. The next answer was neon. Okay. How many electrons does neon have? 10 electrons. Okay. And I asked this question in a very particular fashion. I said, what atom matches the electron configuration of the procedure we just went through? So let's go back with what we started with. What did we start with? Nitrogen, which we said had 7 electrons. What did we do to that atom? We added 3 electrons. What's the identity of the element? Nitrogen. We did not change the number of protons. It cannot be neon because I still have the exact same number of protons that I started with, which takes me to nitrogen. Okay, so answer C ends up being, whoops, not an N. Never mind, we started with nitrogen. N is our symbol. But what's the problem with writing N?
It's not the right charge.
That N has 7 electrons. How do you know it has 7 electrons?
There's no charge.
Where's the charge written?
At the top.
In the upper right-hand corner, nothing is written, which means the charge on that symbol is 0, which means I have 7 protons and 7 electrons. But my electron configuration says I have 10 electrons. So this symbol is incorrect. What do I need to add to it to fix it? Okay. I need to account for the extra electrons. Okay, I added 3 electrons. So, right, I can just say, 3, right? There's 3 electrons. We have to recognize the charge. So when we talked about our subatomic particles, I said one of the critical aspects that you needed to know was the charge on a proton, charge on electron, charge on neutrons. Why? For this very reason. If we add electrons, yes, we're doing a positive, so we might think adding something, but what is the charge on an electron? Negative. We're adding negative to this, which means the charge becomes -3. Okay. This could just as equally be written N3 minus. Okay. I personally find the 3 minus confusing because I look at that and I see a +3. Okay. I want to be able to look at the upper right-hand corner and get an idea of what happened. A negative means more electrons. How many more electrons? 3 more electrons. Okay. If I put the number first, I lose track of what's happening. Believe it or not, I'm alone in this, because you look at the textbook will reference the number, then the charge, which I think is dumb. But
so when you ask us to, like, say, add 3 electrons to nitrogen, are we supposed to write out like the electronic configuration for it, like the new one, or?
So to answer this question, so we started with the electron configuration for nitrogen, and I added a second question. Add 3 electrons, tell me what the electron configuration is. So you needed to write it out, because that was part of the question. What was the last question?
What's the answer?
What is the symbol for what we just described? Well, the symbol is recognizing that we have to have 10 electrons, so we have to find an element that matches 10 electrons. Okay? But we also have to realize that we did not change the number of protons. So our symbol needs to be N, and we have to account for those extra 3 electrons with the charge. Neon, while it may have 10 electrons, doesn't have the proper number of protons for what we just walked through. Kind of make sense? Yeah.
Would you accept, if you asked that, would you accept an abbreviated version of the electron configuration? Like, let's say you use one that has more electrons, like chlorine.
Can you use the noble gas notation? Yes. Okay, so you can put brackets. If I asked you for the electron configuration for iodine, it's going to suck to fill in 53 electrons. You could use the noble gas notation and jump to, where are we, krypton, okay, and then fill in whatever's left over. Okay, that's really low on the periodic table. That's a lot of typing for me. Probably not going to happen. Okay, so that's the idea behind our electron configurations. Okay, we had the fill pattern, which we already discussed. I'm not very good at drawing straight lines, so I don't find this helpful. I try to use the periodic table as my guide for going through and doing it. One of the things that's going to become relevant, particularly for Lewis structures, is recognizing your valence electrons. So let's again look at the nitrogen electron configuration because it's short. The valence electrons are the outermost electrons, okay? The outermost energy level electrons. So when we look at the electron configuration for nitrogen, what's our outermost energy level? Okay. 2p gives me two pieces of information. One, the energy level, and two, the type of orbital. What did I ask for? Asked for the energy level. So you're giving me more information than I asked for by specifying 2p. This is a very hard question or a very hard process for a lot of people to understand and go through. Answer the question that is asked, not the question that you want to answer. What is the outermost energy level for nitrogen? 2. That's the outermost energy level. It's 2. Anything with a 2 in front of it is representing orbitals in the outermost energy level. How many electrons are in the outermost energy level? 5. What are the valence electrons for nitrogen? 5. So we can do it from our electron configuration, but it is also explicit, not quite explicitly, but it is also directly shown on the periodic table. If we take a look at nitrogen on the periodic table, for those of you in the middle, it's probably going to be difficult to see, so the outside people can help out. Find nitrogen on the periodic table. Look at its column number. Column number, 7 is its atomic number. So its column number, hopefully it doesn't say 7 on that. It says 15 or Roman numeral 5. What does that Roman numeral represent? The valence electrons. Your periodic table sort of explicitly tells you the valence electrons. So how many valence electrons would I expect for selenium?
6.
I find selenium with the symbol Se, and I look at its column. 6. How many valence electrons does selenium have? 6. What is the electron? Do I really want to do that? I'll write it out. What is the electron configuration for selenium? Okay, this is going to have to take multiple lines because I don't think I can squeeze it all in there because it's freaking 34 electrons. So it was a bad example to pick, but we'll do that one too. So for selenium, we'd start putting our first electron in. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Why did I not jump to the d orbitals? I'm not there yet. That's what the periodic table does for me. It fills it in accordingly. 4s2. Thankfully, I'm getting there, though. 3d10. 4p4. What is the outermost energy level for selenium? How many valence electrons are in the outermost energy level? 6. Straight off our electron configuration. You'll notice that we skipped the d orbitals. Okay. The reason being is largely where this was primarily used, which is in Lewis theory. Okay. And the video kind of address some of those features. Okay. That was a lot to write out. Can I simplify it? All of these were fully filled and described. Blue's a bad color. Oh, that's not too bad today. All of those were already fully filled. Okay. The electron configuration presented within those blue brackets happens to represent what element? And I now have an equivalent electron configuration. without having to show all those extra pieces. Okay? Depending on your preference, you can use either one. For more advanced general chemistry classes, you'll likely use the noble gas because they will ask questions with lots of electrons. For the sake of this class, I'm probably not going to go beyond the third row, which means using the noble gas notation is pretty meaningless. Okay? Yes?
What did you say the little brackets in red were?
That was attempted to be an arrow.
Yeah.
Those were our highest energy,
Oh.
our highest energy level. We can count the electrons in that equals our valence electrons. How are we doing? I heard a great, really? Okay, cool. We'll accept that and move on. Chapter 5. So we go back to chapter 5. This is where we have our S, P, D, and F blocks. Okay, so here they're colored differently so they stand out. Okay. Why do we not color the big periodic table on the wall? It gives too much information away to students trying to solve stuff. Quite frankly, that's probably what it comes down to. Okay, so what you can do is envision those cutoff lines, those boxes, narrow that in. Okay? So here we go, that's fun. Let's do a quiz. Let's see what you guys can come up with for this. I'll give you like 3 minutes. City. Okay. What we need to do is come up with some kind of way to simplify. So everybody panics and looks at a question, I don't know how to answer that. Okay, well, look at what's given. What can you tell me about all of those things? They're in the same column. What else can you tell me? What do you mean? I like what you're saying. You're saying potassium goes in there. So you do know something, but you didn't tell me the description. What are all these? These are all described as the symbol for the element. Are you given symbol?
No.
No. So what's an easy first step?
K.
Make potassium a symbol. What is the symbol for potassium? Now compare K to everything else you've got. You now have a simple comparison allowing you to think and process through. Okay? Find the patterns. It's not jumping to the answer, it's finding a pattern and working with it. In a multiple choice test, you'd probably get 2 multiple choice answers that were somewhere below lithium. You'd probably get 2 that were above cesium, and you'd get 1 right between sodium and rubidium. What's your answer? 1 right between. Okay? Make sense? How many electrons fit in one p orbital?
6.
Okay. We try that again. How many electrons fit in the d orbitals?
10.
Okay, so why am I getting a big loud 10 for that, but I got a really quiet 6 for this? Does anybody challenge the 6? Somebody should challenge the 6. You happy? There we go. Oh, you're saying the other one. Sorry. Yeah. I'm with you now. You're saying this one. So what does that mean?
Okay, I think I just got it. So when you say p orbital, it means just that one orbital, not the entire shell.
The question very clearly states one p orbital.
Well, there's multiple.
There are multiple orbitals for the p type. You were not asked for multiple orbitals. You were asked specifically for one singular.
So we could choose which one. Oh, just.
Which p orbital are you going to choose?
Oh.
Pick any one of them. How many electrons are there? 2. Your p orbital can only hold 2 electrons, period. Doesn't matter the orbital, it holds how many electrons? 2. If we look at the type of orbital, can orbital types hold more than 2 electrons? Yes, because an orbital type can have multiple orientations, which means multiple orbitals. Okay. I heard a couple I get it. You may be exceedingly frustrated with the phrasing on that, and I don't blame you. I don't agree with this kind of question philosophy, but I've seen it pop up, say, in standardized testing. Like the final. Okay? So read the question carefully, answer the question that's asked, not the question you want to answer. Okay? Why does atomic radius increase down a column? It gets bigger. Okay. So it gets bigger because it gets bigger. That doesn't quite work as a definition. We need a better explanation than that. We have more electrons, and as we go down a column, what happens? Not even more orbitals. It's easier than that. More energy levels. Where are the energy levels? Further away from the nucleus, which means we get bigger as we move down a column. So it's not a statement of saying more electrons. It's a statement of saying larger orbitals or larger energy levels. What happens when we move to left to right? Why does it get smaller to the right? Okay, what was that? So I'm hearing more pull. What does that mean? How do you get more pull?
The protons are pulling in the electrons.
Okay, so you're saying as we move left to right, we have more protons. Yes?
No more.
Left to right, we have more protons and we have more electrons. As we move left to right, we have more protons, and because of that, it gets smaller. What happens if we move hydrogen to cesium, to the number of protons? There are more protons. Your explanation on the left to right doesn't hold true if we go back and look at the up-down. When we go up-down, what changes? The energy level. What happens to the energy level when I move left to right? It doesn't change. So if I'm placing the electrons at the exact same energy level, what should happen to the size? It should stay the same. Okay? Remember, if we look at our size, here's energy level 1, here's energy level 2. I put an electron into energy level 1, what happens? We got a defined size. I put a second electron into energy level 1, what happened to the size? Where did my hand move? Nowhere. What happens when I put another electron in and go up to energy level 2? Did my outermost electron get further away? Yeah, I'm moving up in energy. If I move left to right, do I change the energy level? No. So our first prediction should be no change in size. Is that what actually happens? No. So now we have to come back to the number of protons. I'm placing another electron at the exact same energy level, which means it does not get further away. But what else do I do as I move left to right?
If you're increasing the number of electrons, aren't you also increasing the number of protons?
Yeah.
So wouldn't that make things a little tighter?
So, well, that's the argument that I said on down the column. Right? If you make that argument, then as we move from hydrogen to cesium, what happens to size? You just said more protons, mine got smaller. Cesium has more protons than hydrogen. So your argument of just the number of protons and electrons is irrelevant. Okay, that does not work. Okay. What we're looking at, let's see if I can draw it on here. So for the recording. There we go. We can go back to this drawing. On that y-axis, what's changing? Energy and size. The further away we get, the higher in energy. Okay, so it is big here. Whoops, come on, pen, work. Big here and small here. What happens if we look at hydrogen? Where's that electron? Its outermost electron go? the first energy level. There's my electron. Where's the highest energy electron for lithium go? The second energy level. So when I move up to lithium, what happened to the size? It got bigger. I'm putting an electron further away. What happens when I go from lithium to beryllium? Where do I place that electron? That exact same energy level. Does my atom get bigger? No, because it's going to the exact same energy. So it should not get bigger. Now the question comes to, why does it get smaller? What else changes when we add that extra electron for beryllium?
Does it make it like tighter together?
We're adding another proton. So it is a balance of where the electrons are being placed and the nuclear charge. When we move up to beryllium, what happened? We added an extra electron and an extra proton. What does that mean? So let's pick and draw on the nucleus, get rid of this energy level. Here's my nucleus. For lithium, it is being attracted by how many protons? That outermost electron. It has 3 protons for lithium. The outermost electron for beryllium is attracted by how many protons? Is the electron going any further away? No. What's happening to the center? Is it becoming more or stronger or weaker? Stronger. There's more positive charge. So I have 2 things that are located the exact same distance, except now I'm pulling harder on one. What happens to that outermost electron? It gets sucked in ever so slightly. So what happens left to right is it's a combination of both the electrons and the nuclear charge. When we go up and down a column, we don't worry about the nuclear charge because where are our electrons going? Further away. Right out of the gate, they move further away because they're going to a higher energy level. Okay? So I'll entertain one question. Is that one question? Nope. So one question, and then we're going to have to move on.
So if you have multiple layers of electrons, multiple shells, won't they repel from each other, causing the inner layers to push closer to the positive, to the nucleus?
So what you're trying to do is make the problem that is complicated as it is more complicated by quantifying the exact distance. Don't do that. If you want to do that, we can talk about that after class, but it's not a good idea. Yeah, it's not a good idea. Stick with this. Keep on the outer side. Okay? Last question. No, that was it. So the electron configurations are what are determining how your radius changes. That is the why. What are you responsible for absolutely? The what? Down a column, what happens to the radius? It's bigger. Left to right in a period, what happens? Smaller. You are responsible for that decision. Okay? The why is an advanced topic. And by advanced, this class is supposed to see that. Do I expect everybody to do that? No. With practice, I do. So how do I differentiate between those that understand this and those that do not? This is a letter grade. Okay? The more advanced the topic, the higher the letter grade. That's how it works. Okay? So, nice little picture of our atomic radii. If you want to go back through it with me after class, you're absolutely more than welcome to do it. You need to know the trends. Okay? It's a complex pattern on the Y. Okay? Which then takes us to our ionization energy. What is ionization energy defined as? It's the amount of energy required to remove an electron in the gaseous state. Has anybody heard of electronegativity? Does that have anything to do with ionization energy? Indirectly. Okay? They are not the same thing. Ionization energy is the energy required to remove it to the vacuum. Remember how we had our lines organizing everything? I take an electron and I rip it away from the structure. What is that energy gap? That is ionization energy. That is different from electronegativity. Okay? In general, what happens? The ionization energy increases as we go from bottom to top. Why should it increase as we go from bottom to top? Everybody loves this figure by now. We're saying from bottom, something like, I don't know, lithium, outermost electron located in the second energy level. Hydrogen located where? What am I trying to do in the ionization energy? Take that electron and put it where? Into the vacuum, which is out here. What is the difference between the vacuum and that energy level? 4. I'll accept that. If we look at the ionization energy for hydrogen, what is that difference? Bigger than 4. That's our ionization energy. Okay. Does that kind of make sense?
I know it's more now.
He picked an arbitrary number. I don't care.
Oh,
Okay. We'll look at a table that I think has the actual numbers. I don't have them memorized. It's again the trend, recognizing the patterns. Okay, so if we go back, this is a dizzying lecture for this. Electron is closer to the nucleus. It's lower in energy the higher up in the table we are, which means it's harder to rip that out. I need more energy. What about as I move left to right? Well, it's going to increase as I go left to right. Okay, why? The atomic radius is smaller. Okay? It matches the exact same deal as your atomic radius. And our atomic radius tracks with the energy of the individual orbitals. Okay? So we see an increase left to right for that same reason. Okay? You'll notice that in both those cases I say in general. Why do I say in general? There are exceptions to this rule. Okay? Because it's not a rule, it's an observation on it. So if we take a look at a chart, so Tanner, you were asking about the exact values. I was hoping this actually had values on it. It didn't. So we can even just still looking at the trend. What happens is we go down a column. So we're starting at that first point, which is hydrogen. So I go from hydrogen to the next element, lithium. What happened to the ionization energy? It decreased. Why? Lithium's outermost electron is higher in energy, which means its distance to the vacuum is closer. Okay? And as we continue to look down a column, that's this bottom line. Notice that it consistently drops downwards pretty cleanly. Okay? Why? That was the easy atomic radius explanation. The more electrons, the bigger it got, because they're putting to higher and higher energy levels. What was the confusing atomic radius explanation? Across, left to right. What happens when we look across? So let's pick that second row, starting with lithium and going to neon. What happens when we move from lithium to beryllium? It goes up. Okay, why would it go up? Hunter, you had a good theory before. What was our explanation? The atomic radius got smaller as we went left to right. So that means the electrons held tighter, which means more energy. Okay? But then what happens when we move from beryllium to boron? It goes down. There's what we would first reference as an exception. Okay, that's weird. But then what happens? It starts going up until we achieve nitrogen to oxygen, and it drops again. What is going on with that? That doesn't make any sense. Why would it drop? The radius is still getting smaller. We don't have more orbitals. Remember, we're in the same row. Let's take a look at nitrogen's electron configuration. It's outermost. We have 2s2 and 2p what for nitrogen? It has 5 valence electrons. I've counted for 2 of them. 3. There's nitrogen. What's the other one I want to look at? Oxygen. 2s2, 2p, 4. Anybody notice anything obvious about those that would suggest why one ionization is different from the other? If you've got one, that would be awesome. I don't see anything obvious.
Oxygen's 2p layer has one electron more than nitrogen.
Okay. But lithium had one less electron than beryllium, and yet the trend still maintained the same.
Because it's E orbital.
For oxygen is full, whereas there's only at each orbital full 2.
When we look at our electron configurations, nitrogen is better represented as 2s2, 2px, 2py, 2pz. How many electrons go into each of those orbitals? One each for nitrogen. Remember, same energy level, we separate them first. What happens when we look at oxygen? 2s2, same deal, 2px, 2py, 2pz. What's our configuration look like then? One has two, the other ones are singly filled. Why is this important for us? In our ionization energy, what are we doing?
Taking off an electron.
We're removing an electron. Okay? I have 3 orbitals for nitrogen that are half filled. How symmetric is that? I have 3 things and they are all occupied. Does that seem symmetric? Yes. Okay. What happens if I remove one of those electrons? It's not symmetric. What did we say about symmetry? Roughly equated to beauty. If we take a look at nitrogen, and it goes through an ionization energy, it starts beautiful. By removing one electron, what does it become? Ugly. Does it want to do that? Would you want to go through a procedure where you were made more ugly? Okay, no. You're going to fight and kick and scream. Guess what nitrogen's doing? Fighting, kicking, and screaming. What happens to its ionization energy? It spikes. If we take a look at oxygen, oxygen has 3 orbitals occupied. One of them is half occupied or fully occupied. How symmetrical is that? Not. What happens if I remove one electron? It's symmetric. I go from asymmetric, i.e. ugly, to pretty. How many of you, given the free opportunity to make yourself look pretty, would accept it? Really? Nobody would want to look better? If we remove the gender bias from it, that's going to be a relatively easy thing to do. So what's going to happen to the ionization energy for oxygen? It's going to drop. So it's the kind of conflicting terms there that allow the ionization energy for nitrogen to spike and the ionization for oxygen to drop. That explains the difference. So when we talk about exceptions, it's a complete and utter nonsense. There is no exception. It's understanding electron configurations. That's what's happening within it. Again, what are you responsible for? The exact trend. Okay? The higher level or the higher order question is why. We okay with that? At least close enough? So our quick wins or runs after that, we'll ignore electron affinity. Electronegativity is not in your textbook. It's an average of the ionization energy and the, what's the other word? Just looked at it, electron affinity. It is the ability for any one of our atoms to grab bonding electrons and bring it towards them. This is stupidly important. Okay? That is a dramatic pause for a reason. Electronegativity explains chemistry. That's it. Okay? We can look at electronegativity, and the other big fun trend is atomic radius. We look at radius and electronegativity, that covers 90% of chemistry. It is just applying those same 2 concepts to different situations. Okay? So when we're looking at electronegativity, they are assigned these numbers. You don't need to know where the number comes from. We just need to know what it means. The bigger the number, the more electronegative. which means a better ability to grab bonding electrons. That's it. Okay. Fluorine is the most, cesium is the least. Last trend you have to memorize. Are there exceptions? Yes. Don't worry about the exceptions. Memorize the trend. That covers 89% of all organic or all chemistry. Yes.
Is that why, so like how it's easier for certain elements to lose electrons than others? Is that how common bonds are formed, like H2O?
Yep. That's exactly right. There was another question? Yeah. Not quite. We'll look at that when we look at Lewis structure in just a second. Last thing we want to address is ionic charges, because we already mentioned this. Isoelectronic. Iso means same. Electronic means electrons. So when we're looking at something that's isoelectronic, we're saying it has the same electrons as something else. Okay, we actually already looked at that. We looked at nitrogen. Right? We had N minus 3. That was isoelectronic with our neon, has the same electron configuration. Why is that important for us? What is special about neon? I heard someone actually already say it. Noble gas. Okay. More scientific explanation, full octet. Let's ignore the octet for the moment. Noble gas. What do we know about noble gases? They don't react. They are hoity-toity jerks that hoard everything else from everybody else. Yeah, there we go, Ramsey. Okay. Why is that important? Do you want to become nobility? Why? Nobility will have tons of money, everything's awesome, life is great, money solves all world's problems. Guess what elements are doing? Exact same thing. They are trying to look like the nobility. We have 3 subatomic particles. Okay, those 3 subatomic particles were protons, neutrons, electrons. What happens if I change the number of protons for nitrogen? It's a different element. So can I change the number of protons? If nitrogen's looking at its life, how do I become the nobility? Can it change the number of protons? Nope, because then it's not the same person. Okay? We don't want to die and then disappear and become nobility, because then we didn't get to experience it as we were, right? Okay? Neutrons. Do the neutrons do anything? No, they're just a glue that holds stuff together. What do the electrons do? They contribute our charge. They contribute to our size. They are the clothes of atoms. What do we do in our everyday life to look like nobility? We dress up. Guess what elements are doing? The exact same thing. They are changing the number of electrons that they have to look like the noble gases. That means that certain elements will carry very particular charges. Nitrogen wants to look like a noble gas. Which noble gas is the closest to it? Neon, I heard helium, there's argon. Argon has how many electrons? I heard an so I paused. Neon. It's okay. Neon has how many electrons? Helium has how many electrons? 2. Nitrogen has how many electrons? 7. So for nitrogen with 7 electrons, it wants to look like a noble gas. What's the easiest thing for it to do? Add 3. Couldn't it lose 5? Yeah. That's a lot of things to do. That's harder. So does it do it? No. Okay. How about gaining 11? Yeah?
Wait, what?
What if nitrogen gained 11 electrons? That would get it to argon. That works. It would still look like argon, but that's way too difficult. So instead, it just looks like neon. How about fluorine? Fluorine has how many electrons? 9. What's easiest for it to do? Gain 1 or lose 7? Gain 1. So what happens to fluorine? It only gains 1. If it gains 1 electron, what's its charge? -1. How do we determine the charge? Not just the amount of electrons. It's the balance of protons versus the electrons. Why was it important to remember the charge on all these particles? Because that determines how we get to our charges. Why is that important? We now know how those molecules will react. If I take a look at nitrogen and throw it into an environment, it's negatively charged. What is it likely to interact with? Positive charge. I now have predictive ability based off of looking at electron configurations. Let's flip the chart. Take a look at lithium. Lithium on the complete opposite side. You already know the answer because it's written there. How many electrons does lithium have? 3. What is lithium going to want to do? Look like helium, neon, or argon? Helium. Why? All it has to do is lose 1 electron and it looks like helium. So what does lithium do? Loses 1 electron and its charge becomes +1. It comes from determining the balance in those configurations and how they align. If you don't like that derivation, cool. I got another trick for you. The first column is all charged 1. Second column 2. Third column 3. Fourth column 4. There's some +4s down here. I forgot those were down there and I'm zoomed in so I couldn't see it. So let me fix that. Try again. I don't know. Next column. We'll address that in just a second. -3. Next column. -2. Next column. -1. Why did it flip from going positive to minus? What happened at carbon? How many electrons does carbon have? 6. 6 to 10 means 4 electrons. 6 to 2, 4 electrons. Which is easier? Who the F knows? That's why it's a question mark. That's why we don't memorize it. Because it could go anywhere in between. Boron and aluminum, what are they going to do? They will always gain 3 because their other, or lose 3 because their other option is gaining 5, which is easier. Losing 3. Okay? So you can memorize the columns. You'll notice that the columns, when we get into the negative charge, they only show which elements. What can you tell me about all of those elements? There are nonmetals. You're required to know the charge on your nonmetals, all of them, okay, except for carbon. As far as the metals, which ones do we need to know the charge on? First 2 columns. Okay, well, the first column is +1, the second one is +2. That wasn't that difficult to memorize. Fortunately, we have 3 more that you have to memorize. Zinc, cadmium, and silver. Zinc and cadmium, both are a +2. Why would I think both of them are a +2? Same column. So once I identify the charge on one, the other one's the same. Silver is +1. You're required to know those charges and those electron configurations. Okay. After that, we've got our big summaries. If you've found the slides, okay, you have this summary. These are what you're responsible for out of Chapter 4. This is what you're responsible for out of Chapter 5. Okay? Those topics will show up on the exam. The last part, electronegativity, should look familiar because we talked about that when we looked at the video for bonding. Okay, which means we now need to bust out the lab manual, which you all brought because I told you to bring it. And we will look at some examples for solving Lewis structures. Good timing. Which one slide? If you couldn't tell in the video already, I am super nitpicky nasty about Lewis structure because I deal with the repercussions of general chemistry teaching it wrong. Because I teach organic chemistry. In organic chemistry, I'm concerned about bonding. Well, what does Lewis structure look at? Bonding. So when you screw up Lewis structure in Gen Chem, it screws me over in organic chemistry. pisses me off. Right? That's why the video was built. That does not make it any easier, so don't be like, well, that was still confusing. I'm not saying it's more or less confusing. I'm saying what this will do is set you up to do well in organic chemistry. Right? So, our rules. We have to total the valence electrons. What did we just talk about in chapters 4 and 5? The valence electrons. We needed to know that to do Lewis structure. Right? You'll then need to choose a central atom. How do we choose the central atom? Least electronegative, or we can change that to metallic if you don't like electronegativity because you didn't memorize that trend. We just talked about that. We will then add the electrons in pairs. Why would we add them in pairs? That's how our orbitals filled. We filled in pairs until we were even energy. So we'll fill in pairs when we draw out our Lewis structure. Right? We'll continue to add the electrons until all of the electrons have been added. Not how many I think should be there, but how many I totaled in step 1. Right? Convert pairs of electrons into a line to represent a bond. If you've seen that method with the lines being for every pair of electrons, that's stupid. And that is recorded, and I may regret that later. Right? But that is an awful, awful technique. You only convert pairs of electrons into lines if they are a bond. Right? No one watches these anyway, so it's not a big deal. The next part is the hardest part. Move non-bonding pairs of electrons between atoms until we've achieved an octet. Octet for 8. Why 8? Lewis was a simple man, and he only looked at the first 2 rows, and in particular he kept his focus at the second row. How many occupied columns are in the second row? 8. There's your octet. Okay, that's where it's coming from. Resonance, if you have to continue taking chemistry, particularly organic chemistry, it will haunt you for the rest of your life. Get used to it now. Last thing, assign non-formal 0 charges by just writing it in the upper right-hand corner of your structure. Okay. So with that, where do you have questions? Is there anything in the slides that you're like, dude, that thing right there, that needed to be explained?
I don't know if it doesn't really have to do with Lewis structure, but it was in the video.
Okay.
I think it asked about